Supporter buildings are constructed in stages: planning, foundation, stacking, and finishing with MEP systems. Among them, stacking is the most crucial and complex stage, as it directly impacts the building stability and construction efficiency. The core first method refers to a construction technique in which the central structure core of the supporter building is built ahead of the outer slabs and perimeter frames. In hybrid structure systems like the Yokohama Landmark Tower, where a reinforced concrete core is combined with a steel perimeter frame, the core first method plays a key role in coordinating different material construction speeds and minimizing workflow interference, ultimately accelerating the overall timeline. Unlike the outer structure, the core is stacked one floor at a time. Pre-assembled reinforcement is combined with embedded plates and lifted into place to form the core structure framework. While rebar work is underway, the ACS formwork system is installed, followed by concrete pouring. Gusset plates are mounted onto embedded plates pre-installed in the core wall, serving as connectors for efficiently joining the future steel perimeter beams. Once the perimeter steel beams are in place, deck plates are installed on top. The core first method strengthens structural stability by completing the building's lateral load resisting system early, offering protection against wind and seismic forces during construction. It also enhances productivity by allowing uninterrupted core work. However, careful coordination is required to prevent excessive level differences between the core wall and outer floor slabs. In the Yokohama Landmark Tower, this gap was strictly controlled to remain within 5 floors. In spur buildings, the core is the primary structural element, resisting both vertical and lateral loads. The Yokohama Landmark Tower features a reinforced concrete core. To ensure vertical continuity of the core walls after each concrete pour, lap splice joints must be precisely prefabricated with accurate lengths and positioning for rebar connections. At the Yokohama Landmark Tower, the reinforced concrete core extended through all 74 floors from before to the 70th floor above ground, making the precision of rebar connections critical to the building's structural safety. When necessary, rebar couples were pre-welded or tied in advance to streamline the process. The prefabricated rebars were placed on lifting jigs, where vertical and horizontal bars were assembled into a grid according to the design drawing. At the Yokohama Landmark Tower, the core wall was designed to become thinner with smaller rebar sizes and tighter spacing toward the upper floors. Even slight changes in the core's floor plan were accounted for by using specially crafted precision jigs to ensure accurate intersections at 150 to 300 mm intervals. Embedded plates for future connection with perimeter beams and other structural elements were also pre-installed during this stage. Once assembled, the large rebar panels are hoisted together with their lifting jigs. After the pre-assembled rebar panels are installed, horizontal bars in areas where prefabrication was not possible, such as panel joints or site-specific joints, are connected manually. Once the hoisted panel is positioned, threaded couples attached to the upper rebar are immediately connected to those fixed on the lower rebar. This couple system provides stronger and more reliable joints than traditional lap splices, maximizing stiffness and continuity at rebar connections. During rebar work, the ACS formwork system automatically disengages and is coated with realism agent. At the Yokohama Rail Tower, the ACS operated on a 3 to 4 day cycle per floor, detaching as soon as the concrete reached the required strength. Once rebar placement was complete, the upper working platform and both the inner and outer ACS units were lifted in sequence to prepare formwork for the next level. The ACS system is an integrated formwork solution that combines safety screens, working platforms, foam panels, and lifting mechanisms to construct concrete core walls and mega columns. After completing rebar placement and concrete pouring on one floor, the system lifts itself to the next level for continuous operation. The ACS formwork was composed of durable foam panels, structural support frames, wear system for foam ties, and lifting lugs for hoisting by tower cranes. To meet the Yokohama Rail Tower's design emphasis on smooth exterior finishes, special care was taken in the surface treatment of the formwork. The lifting lugs enable efficient hoisting of the modules in coordination with the tower crane. After each concrete pour and curing, the platforms were lifted to the next level using hydraulic equipment. The lost shoe anchors were retrieved and reused in the next cycle. The assembled ACS platforms were transported to the lifting zone by forklift and then hoisted using a large tower crane capable of high-rise operations. The inner platforms were precisely secured to the shoe anchors and suspension shoes embedded in the core wall. Once platform installation was complete, the ACS formwork units were lifted and mounted onto the platform frames using the tower crane. After the pre-assembled wall reinforcement was installed, the ACS formwork was manually aligned into its final position. Tie rods were then inserted through the wear system to securely fix the formwork in place. The climbing profile is equipped with two lifting mechanisms, upper and lower, and a hydraulic cylinder. Powered by hydraulic energy, the cylinder pushes the upper mechanism upward, engaging its claws into the profile grooves. The lower mechanism then pulls up, re-engaging its claws, allowing the ACS platform to climb to the next level. This lifting process was carried out only after at least 1 day of concrete curing and achieving a compressive strength of 10 megapascal, ensuring both structural safety and construction efficiency. The floor system of the Yokohama Rail Tower was realized using composite slab technology. To form the outer floor slabs, deck plates were installed over steel beams. Stud bolts were welded onto the beam tops, and end plates were placed at the slab edges. The key to this method lies in achieving composite action, where the concrete slab and steel beams act as a unified structure through shear connectors like stud bolts. This integration leverages the compressive strength of concrete and the tensile strength of steel, allowing for thinner section while ensuring both stubbornness and cost efficiency. Stud bolts were welded onto the steel beams, serving as shear connectors that structurally integrate the deck plate, slab concrete, and steel beams. In support buildings like the Yokohama Rail Tower, these connectors play a crucial role in enhancing resistance against lateral loads. End plates, shaped to match the slab profile, were installed at the edges of the deck plates to prevent concrete from spilling outward during pouring. To connect the composite slab to the core wall, rebar from the deck plate was tied to pre-installed rebar couplers or embedded plates within the core. Since the Yokohama Rail Tower adopted the core first method, embedded plates were pre-positioned in the core wall to align with each floor beam. If positioning errors or level deviations rendered these connectors unusable during concrete placement, chemical anchors were installed instead. This process involved drilling, cleaning the hole, injecting adhesive, and inserting rebar to the specific depths. Such connections were essential to ensure structural integration between the slab and the core wall. The composite slab consists of a structural combination of steel beams, deck plates, and concrete. In super buildings using the core force method, each floor beam must be connected to the core wall. To enable this, embedded plates were pre-installed in the core wall at every beam location. In the core force method, embedded plate technology involves pre-attaching steel plates to reinforcement before concrete is poured. This technique serves as a crucial interface between concrete and steel, enabling strong and precise connections between the core walls or mega columns and the perimeter steel beams. For smaller embedded plates used in the core walls, they were pre-attached to the rebar at the prefabrication yard and lifted together as part of the pre-assembled rebar panels. This method reduced lifting time and improved construction efficiency by eliminating the need for separate hoisting and installation of the plates. Before the ACS was lifted, gusset plates and support angles were welded perpendicular to the embedded plates in the core wall at the low levels, typically between B2 and B3. This pre-installation avoided the need for high elevation work after the ACS was raised. These components later serve as critical supports for connecting the perimeter steel beams to the embedded plates. As the structure was assembled in 3 floor units, steel connection techniques were used to link columns within each unit, including the critical connections between the perimeter core walls and the outer floor beams. The vertical columns of the Yokohama Landmark Tower were hoisted and installed in 3 floor units. To connect the upper and lower columns of each unit, column plates were welded to both ends. 2 splice plates were then placed on either side of the joint and bolted together, allowing the columns to temporarily stand independently. Following temporary assembly, full penetration welding was performed between the upper and lower column sections. As this joint transfers the full axial load of the structure, it requires advanced welding techniques and strict quality control. Once welding was complete, the temporary column plates were cut away, finalizing the monolithic column connection. This method was essential for ensuring vertical continuity and stable load transfer in a superstructure like the Yokohama Landmark Tower. To improve construction efficiency, the cutwork system was installed in 3 floor units. When installing the cutner, the mega crane positioned on the core handled the lifting operations. Its location was carefully planned based on the hoisting paths and final installation points of each unit. This method differed from conventional lifting using small hoists 2 floors above the installation level. The N+1 floor served as the cutner assembly deck for panels to be installed on the nth floor. For example, the 9th floor functioned as the assembly level for cutner units to be installed on the 6th, 7th, and 8th floor. At this level, panels were unpacked and fully assembled into complete units before installation. Installation was carried out by fastening the cutner panels to pre-embedded floor anchors and fasteners located at the edge of the outer slab. These fasteners featured elongated bolt slots, allowing for fine adjustment and precise alignment. Rubber gaskets installed at the top stack joints of the lower panels ensured a tight seal when the upper panels were placed, securing the Yokohama Landmark Tower's facade against air and moisture infiltration while enhancing insulation performance. In super buildings like the Yokohama Landmark Tower, lifting large exterior panels exposed to strong coastal winds required precise control to prevent unwanted rotation. To address this, a specialized thruster-assisted device was developed. by manipulating the thrust force generated by two fans attached to the lifted rod. The system actively controlled the panel's azimuthal rotation around its vertical axis. This technology was essential for safely and accurately installing large curtain panels at great heights. The 51st floor served as both a mechanical space and a structural transition zone, optimized for installing the outrigger system. With embedded members in the core were connected to the perimeter frame via diagonal braces. This level enabled effective load transfer and enhanced resistance to seismic and wind forces. In the Yokohama Landmark Tower's dual-tube structure system, the steel columns and beams forming the outer tube serve as external connection points for the outrigger system to accommodate connections with diagonal braces and other outrigger components. Specialized steel members were either embedded or outfitted with designated connection joints. During concrete placement for the core walls on the 51st mechanical floor, key outrigger components, upper cores, lower cores, and vertical members were pre-embedded into the structure. The outrigger lower cord was embedded within the core wall, with stud bolts welded along its sides to ensure composite action with the reinforced concrete. Similarly, the upper cord was also embedded, supported by vertical steel columns. Stud bolts were welded to the side of the upper cord as well, enhancing its bond with the surrounding concrete. The large outrigger braces of the Yokohama Landmark Tower were fabricated in two segments to improve transport and high-rise lifting efficiency. A delay joint method was used, in which final welding was performed only after initial concrete deformation has stabilized, minimizing residual stress in the structure. The outrigger braces were installed in two segments. The lower end was connected to the joint of the first brace segment, while the upper end was joined to the embedded connection point of the outrigger's upper cord within the core wall. These connections followed the same welding method used for column splices. In particular, the connection between the second segment of the outrigger brace and the upper cord was treated as a delay joint. This approach allowed deformation from lateral loads to stabilize before final welding, minimizing residual stress and optimizing structural performance. The connection between outrigger members is carried out in the same manner as column welding joints. Plates are welded to the ends of each outrigger member, and a splice plate is temporarily bolted to these plates to support the structure independently. Then welding is performed on the upper and lower outrigger member base materials. After the welding is completed, the member end plates are cut off to finalize the joint. The Yokohama Landmark Tower was constructed with precision, using advanced layer-by-layer building techniques tailored to each floor's structural role. Through this customized stacking method, the tower achieved both structural integrity and construction efficiency, rising safely to its full height of 296 meters over 70 floors.